Okay, folks, let's talk about this wild idea that the whole universe is stretching, getting bigger every day. You know, people often picture some enormous explosion throwing everything outward from a single point, but that's not quite right. It's more subtle, more interesting. Imagine you're sitting in your kitchen watching bread dough rise. The raisins in the dough don't move on their own. They stay put relative to the dough, but as the dough expands, the raisins drift farther apart. No center, no edge, just everything getting more space between it. That's closer to what's happening out there among the stars. Back in the late 1920s, Edwin Hubble was up on Mount Wilson with that big 100-inch telescope looking at fuzzy patches we now call galaxies. He noticed something funny. The light from those distant galaxies was stretched, shifted toward the red end of the spectrum, like the sound of a race car dropping in pitch as it zooms away from you. The fairer the galaxy, the more the light stretched, meaning the faster it was receding. Hubble plotted distance against speed, and it fell on a straight line. Velocity equals some constant times distance. We call that constant h today, Hubble's constant. It's around 70 kilometers per second per megaparsec. Don't worry about the units, just know it's a measure of how fast things pull apart. If you run the movie backward, everything comes together. Galaxies get closer, denser, hotter, keep going, and about 14 billion years ago, all the stuff in the universe was crammed into a tiny, incredibly hot region. That's what we call the hot Big Bang phase. But notice I said phase, not the absolute start. We'll come back to that. Now, why does gravity work the way it does? Einstein figured it out in 1915. Gravity isn't some mysterious force pulling across empty space. It's the shape of space and time itself. Picture a trampoline. Put a bowling ball in the middle. It sinks, curving the surface. Roll a marble nearby, and it spirals in. Not because the ball pulls it, but because the path is curved. That's general relativity. Mass and energy tells space-time how to curve, and curved space-time tells mass and energy how to move. In the universe on large scales, that curvature plays out in the expansion. Alexander Friedman, a Russian mathematician, took Einstein's equations in the early 1920s and solved them for a universe filled evenly with matter. He found the whole thing could expand or contract, depending on how much stuff was in it. The scale factor, think of it as the average distance between galaxies, changes with time. The rate of change depends on density. For ordinary matter, density drops as the cube of the scale factor. Radiation drops even faster, as the fourth power. People wondered back then if the universe was static, unchanging. Einstein even added a fudge factor, the cosmological constant, to keep it steady. But Hubble's observations showed it wasn't steady at all. It was expanding. In the 1940s and 1950s, there was a big debate. George Gamow and his students pushed the hot Big Bang idea. They said the early universe was a scorching soup of radiation and particles, cooling as it expanded. Gamow even predicted that light elements like helium should form in those first minutes. Observations matched about a quarter of the universe's mass as helium, cooked in that primordial fire. On the other side, Fred Hoyle, Herman Bundy, and Thomas Gold proposed the steady-state theory. Beautiful idea. The universe looks the same forever. No beginning, no end. As it expands, new matter pops into existence to keep the density constant. Perfect cosmological principle. Same everywhere, same always. Hoyle was brilliant, and he fought hard for it. We had lively arguments about this in the physics world back then. But nature picks sides. In the early 1960s, radio astronomers started finding strange sources, quasars, only in the distant ancient universe. No quasars nearby. That meant the universe changed over time, evolving. Steady state couldn't easily explain that. Then came the knockout punch in 1965. Arno Penzias and Robert Wilson at Bell Labs were tinkering with a bighorn antenna meant for satellite communications. They kept picking up this annoying hiss, uniform, from every direction, day or night. No matter how they cleaned the antenna, even chasing away pigeons, they couldn't get rid of it. It corresponded to a temperature of about 3 degrees above absolute zero. Nearby at Princeton, Bob Dick and his team were building an experiment to look for exactly that, leftover heat from a hot early universe. Gamow had predicted it years earlier. When Penzias and Wilson heard about it, they realized they'd stumbled onto the cosmic microwave background, the cooled glow of that primordial fire. Everywhere you look, the sky shines faintly with microwaves, perfectly matching a black body at tiny ripples in it, 1 part in 100,000, match what you'd expect from slight lumps in the early soup that grew into galaxies. Steady state had no natural way to produce such a uniform glow. Big Bang did. By the late 1960s, most physicists accepted the hot Big Bang model. The universe started dense and hot, expanded and cooled, formed atoms, stars, galaxies. Run the second law of thermodynamics, entropy increases, things get more disordered. Coffee cools, eggs scramble, never the reverse. The arrow of time points toward higher entropy. Yet the early universe had incredibly low entropy, very ordered, very smooth. Gravity likes clumps, but everything started spread out evenly. If you crunch the equations backward, using general relativity, you hit a singularity, density infinite, curvature infinite, time zero. Roger Penrose and Stephen Hawking proved theorems in the late 1960s and 1970, showing that under reasonable conditions, expanding universes like ours must trace back to such a singularity. In my lectures to freshmen, I always pointed this out. The laws of physics describe how things change, but they don't explain the initial setup, why low entropy, why these particular conditions. Physics equations are time symmetric. You can run them forward or backward, but the boundary condition at the start is special. Think about it like this. Imagine ants crawling on the surface of a balloon. As you inflate it, the ants move apart. No ant is at the center. The center is inside the balloon, not on the surface. Our universe is like that surface, finite but unbounded, or maybe infinite. The expansion isn't into something outside, space itself stretches. Integrate that, and you get the age of the universe, roughly 1/h, about 14 billion years. But near the singularity, the math blows up, derivatives go infinite. Classical physics stops making sense. Quantum effects must kick in at tiny scales, the Planck length, where gravity meets quantum uncertainty. Vacuum isn't empty, it jiggles with virtual particles. Maybe those jiggles got stretched in the expansion, seeding the ripples we see in the microwave background. We don't know what happened before or at the singularity. Maybe the laws break down, maybe there's no true beginning, perhaps a quantum bounce or something else. But the hot Big Bang describes everything from a fraction of a second onward, beautifully. Look up tonight. Those stars, those galaxies, they're all rushing away. The light we see left them millions, billions of years ago. We're looking back in time. And that faint microwave hum, it's the echo of the universe's fiery. The real excitement is that we can figure this out piece by piece, observation by observation. Nature's clever, but so are we. Keep asking questions. That's how we learn. Okay, now let's dig deeper into this puzzle. We've got the universe expanding from a hot, dense state, with that microwave glow as a souvenir, and those tiny ripples hinting at seeds for galaxies. But classical gravity takes us back to a crunch, curves going wild, everything infinite. Penrose and Hawking showed in the late 60s and early 70s that you can't avoid singularities in reasonable setups. Run the equations backward, and bam, you hit a wall where physics, as we know it, stops. It smooths things out with uncertainty. Remember, even empty space isn't empty. Heisenberg tells us you can't pin down position and momentum exactly. There's always a jiggle. Particles pop in and out on borrowed energy, as long as they pay it back quick. In my QED work back in the 40s and 50s, we tamed those infinities in electromagnetism. Scale that up to gravity at tiny Planck length, about 10 to the minus 33 centimeters, and who knows what happens. At those scales, space-time might foam or loop, avoiding the sharp singularity. John Wheeler talked about quantum foam in the 50s. Maybe the universe bounces instead of crunching to nothing. Or perhaps there's no true edge, just quantum paths summing over histories, like in the path integral approach we use for particles. They're not random noise. Quantum fluctuations in the early soup got stretched. Think of the vacuum wobbling, tiny energy differences here and there. Expansion freezes them in, like wrinkles on a balloon as you blow it up. Those become density lumps, pulling matter into galaxies over billions of years. Back in the 70s, folks started mixing quantum fields with gravity more seriously. Hawking showed black holes aren't totally black. They glow faintly from quantum effects near the horizon. Particles tunnel out, evaporating the holes slowly. That ties entropy to area, a big clue for quantum gravity.
For the whole universe, similar ideas float around. Maybe the low entropy start isn't so special if quantum effects erase the singularity. Or perhaps the arrow of time, why eggs break but don't unbreak, ties to the expansion itself. In my lectures, I always said the second law needs a special past condition. Things started ordered, smooth, gravity makes clumps, increased disorder overall, even though locally it pulls together. Why so smooth at first? That's the flatness problem. Why isn't the universe more curved or crumpled? And the horizon problem. Why do opposite sides of the sky match in temperature when light couldn't have traveled between them to even things out? Ideas bubbled up in the late 70s and early 80s to fix this. A brief superfast expansion phase, faster than Hubble's regular stretch, could iron out wrinkles and make distant parts communicate early on. Quantum jiggles during that phase get blown up huge, matching the observed ripples. It was exciting times. Particle physicists chasing grand unification ran into issues like too many magnetic monopoles, defects that should have flooded the place but didn't show up. A rapid stretch dilutes them away. False vacuum energy, like a temporary cosmological constant, drives the push. The math is Feynman again, but with extra drive. The scale factor grows exponentially, at like e to the ht, doubling size ridiculously fast. Integrate the density contributions and radiation or matter dilute quick, but vacuum energy stays constant until it decays. After that burst, it reheats into the hot soup we know, nucleosynthesis kicks in, and we're off to the standard picture. Entropy gets a boost too, explaining the arrow without too contrived a start. But is there a true beginning? Quantum cosmology tries wave functions for the universe itself. No boundary, a tunneling from nothing. Time emerges from imaginary parts, like in thermodynamics. Wheeler and I toyed with time-symmetric ideas back then, advanced and retarded waves, balancing. Perhaps cycles expand, crunch, bounce quantumly, repeat. Entropy resets somehow, or carries over. Oscillating models were around in the 50s, Tolman and others, or eternal inflation, pockets keep bubbling new regions forever. Our bang, just one phase change, in a bigger foam. The joy is we don't know yet. Laws describe change beautifully from early times on, but the ultimate origin may be evolving laws, or just how quantum probabilities play out. In gravitation lectures around 62-63, I wrestled with this. Total energy zero, positive matter cancelled by negative gravity potential. Creation from nothing costs zilch. Look at it, universe breathes out, cools, structures form. You're here, atoms from ancient furnaces, pondering it all. The real kick is guessing nature's game. Testing predictions, microwave maps show those predicted ripples, future scopes hunt gravity waves from that era, or finer patterns. No final answers, just better questions. That's physics. Doubt, wonder, chase the unknown. Go out, stare at the sky, it's vast, ancient, connected to you. Questions bubbling. Good, that's where discovery starts.